We've got the idea now of trig ratios. Let's go back to the original question that we asked at the beginning of today. And it says, how much or how many items out of the original 6, given any triangle, do I need in order to be able to calculate everything about the triangle? And so I'm now not just looking at right angle triangles, I'm looking at any triangle whatsoever. And it turns out that what you need to know is 3 things, same as we had before. So I need to know 2 sides and an angle, or 2 angles and a side, but I need to know 3 things. Once I know those 3 things, I know everything. And the way I move from knowing 3 to knowing everything, we've got a couple of rules. And the first rule is the cosine rule. And so this one is super important. And it's this. Where does it come from? Well, first of all, I guess I should say this. It says, if I'm given 2 sides, in this case B and C, and the included angle, in this case A, so you can see in the picture here, angle A is included between sides B and C. Okay, so I need the included angle to use the cosine rule. But given 2 sides and the included angle, then I can work out the third side. I can work out this side A. Can work out the remaining side. i.e. A. Where does this rule come from? I'm not going to go through the proof, but what I will say to you is this. The way it's worked out is we split this thing up here into 2 right angle triangles. We know about trigonometry in right angle triangles, and we've got a side H there, or H for height in that case. And what I do is I work in that triangle, I work in that triangle, and then I eliminate the H. And when I do all of that, this is the formula I come out with. And interestingly, if you think about it, in a right angle triangle, if I know 2 sides, or 2 sides here, I can work the third side out via Pythagoras' theorem. Sitting in here is something looking very like Pythagoras' theorem, but it's generated because of this angle sitting in here. So this is sort of a more general form of Pythagoras' theorem, if you like, sitting in here. It enables us to work out the third side given 2 sides. The other possibility, I guess, for this is that if I am given 3 sides, then I can work out an angle. I can work out an angle because I can rearrange this. I can make cos A the subject of that. So what I'm going to do is I'm going to take B squared and C squared over to that side, and then I'm going to divide by 2BC. So if I do that, I get cos A is equal to B squared plus C squared minus A squared over 2BC. That's the same rule, just written with cos A being the subject. And the thing is, I could call that angle side A, angle A, or I could call that angle A, or I could call that angle A. So given that I have 3 sides, I can actually work out all 3 angles. So if I know 3 sides of the triangle, I know everything about the triangle. In there. So let's use the cosine rule. As I say, you would obviously have this written on your cheat sheet, would you not? Yes, you would. It's looking more and more like you need more than 1 page on your cheat sheet. I suggest you might need to write small. Okay. You're allowed one sheet both sides. Sorry? A4, unfortunately, yes. Yes. I have seen people write in one colour in one direction and then another colour in another direction too, but it didn't work because they couldn't read it. So, but anyway, they tried. All right, here we go. So it says, here's a triangle. We've got two sides and the included angle, so therefore we should be able to work out the third side. So, when you see two sides and the included angle, you will immediately think cosine rule. And in terms of the cosine rule, this x is going to be my a, so this is going to say x squared is going to be 1.2 squared plus 3 squared minus 2 times 1.2 times 3 times the cosine of the included angle, which is 73 degrees. So all you have to do is substitute into the cosine rule and you are done. Get out your calculator, make sure you can do that, and I got something like 8.3349 to 4 decimal places. And so x will be the square root of this. The positive square root because it's a distance, and my calculator gave me something like 2.8870 to 4 decimal places. I would suspect in any practical application, given that we've only measured this side to 1 decimal place, we'd probably only work this out to 1 decimal place as well. But anyway, for the moment, just illustrating the use of the cosine rule, there it is. But the important thing for you to recognise here was I had two sides and the included angle. If you do that, substitute straight in. Now, in the second example, we're actually given two sides, but we're not given the included angle. So the cosine rule looks a little bit tricky at this stage. And it turns out, look, I could use the next rule and I could do a sequence of calculations, but I can in fact use the cosine rule in this case as well. It's not so straightforward, but let's go through and do it. So in here, so let's use the cosine rule. So by the cosine rule, and as I say, this may or may not be the best way to do this one, but we can do it using this cosine rule. The cosine rule refers to two sides and then the included angle. And so in this case, my a here is 3. So this is going to be 3 squared is going to be b squared plus c squared. And I've got to put my unknown in there. Minus 2 times 1.2 times x times the cosine of the included angle. And so what I have here is a quadratic equation in x now. I've got x squared, I've got this number here involving x, and then I've got this term over here being the constants. So when I rearrange this, I will have x squared minus, now I work out 2 times 1.2 times cos 73, and when I do that I get something like 0.7017, and that's just an approximation in there, x. So that is just an approximate value for that coefficient sitting in there. And so I've got that minus that. Then I'm going to have 1.2 squared minus 3 squared. And so that comes out to be 7.56, and that number's actually exact in this case. Because that only has one decimal place, when I square it I'll have two decimal places, and so my answer will have two decimal places. So that 7.56 actually turns out to be the exact value of that one. But that's just fortuitous in there. And so therefore I have a quadratic equation which I can solve via the quadratic formula. So I would say to you, solve via the quadratic formula. And here A would be equal to 1, B would be equal to minus 0.7017, and C would be minus 7.56. And so your quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. In there. So just substitute those numbers into that and you will get, therefore, x is equal to negative b plus or minus the square root of b squared minus 7.017 squared minus 4 times a times c. Now I'm going to turn that into a plus because my c was negative. Make that go all the way there. All over 2 times 1. And you get two answers. And I'll just write them. Oops, that's not even the right one. I've got 3.1 to 1 decimal place and minus 2.4. Clearly we're not interested in the negative answer in this case because I know x isn't negative, and so we conclude out of that that x is approximately 3.1 in there. So it is possible to use your cosine rule, I should say, in this particular case. I guess you need to be proficient in using your calculator in there. So conceptually it's straightforward. Get a quadratic equation, solve it. It's just that it's easy to make a slip up in the arithmetic in there, that's all. That's all you need to be careful of. So, if we've got two sides, using the cosine rule enables us to calculate the remaining things that we don't know. If, however, we have two angles on one side, then we can't use the cosine rule, and in which case I need to use what's called the sine rule. And that's this one. And once again, it comes from the same sort of idea of splitting the triangle up into right angle triangles. And so wherever you write the cosine rule, you'll also write the sine rule. And this one says in here, this is actually one equation, two equations, three equations. So there's actually three separate equations in there, if you like. A over sine A is equal to B over sine B. A over sine A is equal to C over sine C. And B over sine B is equal to C over sine C. So you use whichever one out of that you actually want. But the thing is, if I have two angles on one side, I can find a remaining side. So this is good when I have given two angles and one side can find another side. That's a good thing to do. For example, in here, I could make A the subject of this. I could say A is equal to B sine A on sine B. So given two angles and a side, I can calculate another side. given angle A and B and little b, I can find little a. Or alternatively, I could be given two sides and an angle, and then I can find another angle. So I can say, or given two sides and an angle, I can find another angle. So using the same equations here, I could make sine, so for example I could say, look, sine A is equal to, how would that go? That'll have to be A on B sine B. And so A would be sine inverse of that. I would use my sine inverse to find A. I guess I could write that there. So A is therefore sine inverse A on B sine B. So they're the ways in which we're going to use the sine rule. Okay, so let's have some goes at that. So it says, let's find the value of x in this triangle, and you can see that I have two angles and one side. Two angles and one side says sine rule. So I can say the ratio of x to sine 73, let's say by the sine rule, I will have the ratio of x to sine 73 will be the same as the ratio of 1.21 to the sine of 22 degrees. So the ratio of a side to the angle opposite, the sine of the angle opposite, are equal. And so that tells me that x will be 1.21 times the sine of 73, all divided by the sine of 22. And then you whip out your calculator, and I got, whoops, that's not degrees, that's length to two decimal places. I got 3.09 in that case. So that would be the length of the side opposite angle 73. And in the last example, I've got two sides and an angle, and I want to find another angle. So again, I can use my sine rule. And it would say the ratio of 3.1 to sine 73, the ratio of 3.1 to the sine of 73 degrees is the same as the ratio 2.13 to the sine of theta. from here, just make sine theta the subject. So this tells me that the sine of theta will be 2.13 divided by 3.1 times the sine of 73. Whip out my calculator, and in here I got a number like 0. I think that's a 6. I think it's a 6.571 to 4 decimal places. And so theta, so I'll come down here, therefore theta is equal to sine inverse 0.6571. And again, I have to use my calculator to do that. My calculator is in degrees. That will be 41.08 degrees approximately. So here I've gone. How do I choose how many decimal places to write down to? I just guess. Sometimes I do 4, sometimes I do 3, sometimes I do 2. The calculations, of course, I always actually keep everything the calculator has. I keep all the decimal places in doing the calculations. It's just when I write them down, I just write them down to whatever I feel like at this stage. I have no reason to choose anything over another at this stage. But anyway, that's our introduction to the trig ratios. What we will do next week is we'll come along and build towards the trig functions.